All right, howdy folks. Welcome back to Professor Carbon. In this video, we're going to go over a slightly more complicated and advanced mechanism. I would largely put this in the category of either ketone reactivity or carbocation rearrangements, depending on how you want to think about it. As I do for all of these advanced mechanisms, what I first try to do is take a peek at my starting material, my product, and see what kinds of things are changing on both sides as a way of kind of mapping out what kind of reaction I need to be looking at. And so as we can see on the starting material on this side, we don't have an aromatic benzene ring, we have a cyclohexane, but we have a cyclohexane over here as well. And thankfully it has the same R and R prime substituents. And so what we can use because of that then is the left half of the molecule kind of as an anchor for our perspective. In contrast, you'll notice that the starting material over here has a cyclobutane, and in the end here it has a cyclopentane. We'll also notice we've gone from a tertiary alcohol to a ketone, although we do still have this five-membered ring kind of dangling off. You'll notice on the other hand, though, it's connected by one bond in the starting material, and it's connected by two bonds in the product. And so something else must have occurred to help make that rearrangement happen. Okay, the next thing I look at is what kind of reagent I have, and in this case it's boron trifluoride, and that is a very strong Lewis acid. And so that Lewis acid is going to typically bind to some Lewis base and trigger a rearrangement. In this particular case, though, what I think we can do is take a look at the hint that's given, and it says hint make H plus first. And really there's only one acidic H, and so that would be the OH, and conveniently for us, oxygen and alcohols are decent Lewis bases, and so they can react with that Lewis acid. So let's just start there and see where we get. And remember, for Lewis acids, if we're going to make the oxygen plus as if it were protonated, then we need something else to be minus. And so formally, the Lewis acid will have a formal negative charge. That doesn't mean it's actually negatively charged. Odds are good that that negative charge exists on fluorine and oxygen, much more than it does on boron, because fluorine and oxygen are the electronegative atoms. But as a reminder, the formal charge is a bookkeeping exercise to really just help us keep track of how many electrons are involved. And in this particular case, boron would have 4 bonds or be tetravalent, and it only has 3 valence electrons. And so we're going to use that negative charge to denote that. All right, let me finish drawing the rest of our starting material here. There we go. So that's good. And then let's just see if we can take that H plus off to generate us some H plus. And as I've said in my other mechanistic videos, I personally am okay drawing H plus just coming on off, as long as we both understand that there really must be a base somewhere in the molecule. And by just drawing H plus kind of floating away, as if you will, or being discharged into the vacuum, which is untrue, what we're really acknowledging is we're not so sure what the actual Bronsted base is. And in many complicated reactions, it's unclear if that Bronsted base is the solvent, if it is a neighboring molecule, or if it's a different functional group, because often our complicated molecules have many, many Lewis bases present in them. Okay, and so in this case then, I'll just again catch up by drawing another part of this molecule. As you can see, it gets a little bit more dicey as we add a little bit more complication to the scaffold. Now we did lose H plus, but we still need to keep that minus on the boron. Okay, so this is the key part here, or at least one of the key recognitions. As a reminder, our alkyl ethers are not so reactive to acid. Yes, they certainly will be hydrolyzed with very strong acid, but what we have in this molecule is an enol ether. And enol ethers are a double bond, so ene and ol, which would be the alcohol from which the ether was derived. And hopefully you can recognize from our keto-enol tautomerization that would be in most textbooks under the ketone chapter that the enol is equivalent to the ketone, and the ketone is at the +2 oxidation state. So overall, this enol ether is going to behave more akin to a ketone. And that's going to be the key step here, because this enol ether is basic not on oxygen, but on carbon. And so we're going to use that to generate. Oh, and I'm actually going to add one additional arrow here just to go directly to the oxocarbenium ion. Again, keeping that negative charge. And again, this now is an oxocarbenium ion. Very key intermediate for a lot of reactions that ketones undergo, including things like acetal formation or acetal hydrolysis. So you definitely want to keep that in mind. All right, now this oxocarbenium ion has a resonance structure. Where it is a carbocation. So we formally move that charge from oxygen to carbon. And of course, the carbocationic form should not be the quote preferred resonance structure, because carbon does not have a full valence. Whereas in the oxocarbenium ion, even though the positive charge is on the more electronegative oxygen atom, which would normally be bad, we do give carbon a full octet and a full valence. And so typically the oxocarbenium ion is the preferred resonance structure. However, the oxocarbenium ion does react and behave as if it were a carbocation. Now, carbocations themselves, we know, can be subject to alkyl shifts, and the most common of which that are taught are either a methyl shift or a hydride shift, so a carbocationic rearrangement. It turns out that that fundamental reactivity is much more broad than simply having only H or only methyl move. In most cases, any adjacent carbon-carbon bond can move over. And in this particular case, because we have this strained cyclobutane ring right next to the molecule, there's a good amount of energy that would be released if we open up or expand that to a more stable ring size. And indeed, that's exactly what's going to happen. So we're going to undergo what is called a 1,2 alkyl shift or a ring expansion. And there's two bonds here that could be expanded. And it's unclear on its surface which one might be more prone to that rearrangement. But we can use the product here as a little bit of a guide to figure that out, because the oxygen-containing carbon needs to be kind of in that second ring and in the middle. And so we need the carbon that is next to this quaternary center to be the one that moves over. And so we can use that as our map. And so this carbon is the one that's going to need to end up bound to this carbon. And so we're going to need that bond to move on over. Okay, and I'm going to draw this in an ugly way first, just so that you can follow me, and then I will try to redraw it in a way that looks more akin to the product. So the first thing I'm going to do here okay, so none of that changed, and then none of this has changed so far, except now we need a carbocation at that carbon, because the carbon I'm going to circle here in green, that's the one that's losing its electrons, so we're going to miss out on that. We're still going to have OBF3. We're still going to have that negative charge on boron because we still have that positive charge on oxygen. Okay, now I'm just going to draw this like so. And now I'm going to put a really ugly bond through here. Okay, and so that was the bond that we would have formed over on the preceding step. So I'll just highlight that in yellow. We broke this bond and we're going to make a bond from here to here. Okay, and so that is going to be this yellow bond. And it looks pretty ugly that way. So now what I'm going to do is just kind of imagine, unugly it, if you will, beautify it. And if you're ever in doubt, I always kind of encourage you to do it in 2 steps like this. It's also a great thing if you're ever confused what's up. You can always number your carbon atoms and then figure out which bonds are being made or broken and then renumber them later on. Certainly for yet even more complicated reactions, I almost find it necessary to have the numbering. All right, so we are going to have our up here to O, and like so, and then we still have our BF3 hanging out, just chilling, still going to be minus, but now we're going to have that plus charge over there. All right, and this, by the way, looks like another carbocation. So the driving force overall for this reaction, again, is going from our cyclobutane to a little bit bigger cyclopentane that has less ring strain in it. But you'll recognize that this, again, is an oxocarbenium ion in disguise. And now at the very end of this reaction, all that needs to happen is oxygen gets its electrons back. We go to the product and we regenerate some BF3. And so this reaction is Lewis acid catalyzed because we come out with the Lewis acid, and that's the same thing we went in with in the first place. Okay, and so in principle, we should be able to use a very small amount of the BF3 and get it to do multiple reactions because it goes into and comes out of the reaction. Again, what I'll encourage you to do is recognize these central oxocarbenium ions and their resonance structures. Ooh, I should actually correct this arrow. That's not a reaction. That is a resonance arrow there. So feel free to be reminded of that as well. Okay, that's it for this reaction. Again, I would place this in the slightly more complicated category, but hopefully for the students that are really looking to master organic chemistry, you can follow along and see that all of these little basic steps are really not anything that's fundamentally different. It's just put in a much more complicated setting. And again, kind of the twist here is one, being able to generate that proton initially. Two, recognize that we have an enol ether that behaves much more like a ketone and importantly goes through this oxocarbenium ion that is our key reactive intermediate. And then we're going to have this ring expansion through the carbocation or oxocarbenium ion. And in this case, I would call it a 1,2 alkyl shift or a ring expansion reaction. So cool. Thanks for tuning in to Professor Carbon. I'll touch base with you next time.